already we have seen between subjects comparison to sample t-test to sample t-test. We got it. Okay, x1 x2 here already we have been seen. X1 x2 are the means from sample 1 and sample 2. S1 S2 the standard deviation from sample 1 and sample 2. N1 and N2 the sample size. Okay, the degrees of freedom for one sample t-test in n minus 1. The degrees of freedom for one sample t-test is n minus 1. For two sample t-test, a simple formula is n1 plus n2 minus 2. Okay. Then, however, the correct formula is given by Welch-Satterwhite procedure. It provides accurate results even if the variance are unequal. If the variance are unequal. TF degrees of freedom TF. Okay, s1 square divided by n1 plus s2 square divided by n2 whole square divided by s1 square divided by n1 whole square s2 square divided by n2 whole square. Then for this here n1 minus 1, here n2 minus 1. If variance are unequal, the result actually here what we will do for n1 corresponding s1 square divided by n1 s2 square divided by n2. Here this is square purpose for scaling purpose. So for this much n1, how much s1? For this much n2, how much s2? Like this, then squaring, getting value add, then squaring. Like this, s1 square same here. Okay, but integer square, then it had to be n1 minus 1. What this is degrees of freedom for one sample test. Okay, and another one sample test like this squaring. Here whole squaring 1 plus 2. Then here 1 square divided by degrees of sample test to one sample, and then another one divided. Then you will get this one, add, then how much we are getting squaring of, then divided by this value, degrees of freedom. CA around the difference, but you have to keep in mind this part. Yeah, x1 cap and the x2 cap are the means from sample 1 until 2. S2 S1 and S2 the standard deviation from sample 1 and the sample 2, and N1 and N2 the sample sizes. N for sample sizes, x2 x cap for means for the sample, s2 for standard deviation. How will we keep in mind? Cap is the that one means yes for standard deviation, and for always sample size only. So keep in mind. Always remember that one. CA around the difference. There are several ways to report an effort size. There are several ways to report an CI around the difference. CI around the difference. CI around the difference. Okay. What is that? There are several ways to report an effect size. Effect size, the most compelling and the easiest to understand is the confidential interval. Confidential CI. The following formula generates a confidence interval around the difference scores to understand the likely range of the true difference between products. The following formula generates a confidence interval around the difference scores to understand the likely range of the true difference between products. True difference between products x1, x2, mean of the sample x1 and x2, that is to be subtract both the sample 1 and 2 mean, okay, plus or minus T alpha into root of S1 square divided by N1 plus S2 square divided by N2. Corresponding standard deviation from sample of size. Sample of size. This one also same. S2 square. Why square means scaling purpose. Okay. That is root square also scaling purpose only. Okay. So for S2, for N2 sample size, S2 how much? 2B, and for S1, for sample size N1, N sample 1 standard deviation divided by that sample size. Standard deviation to be squaring, then getting value to be added both sample 1 and sample 2, then to be squaring, sorry, rooting. Root means this value will be reduced, then T alpha multiply, then how much we got means from sample 1, sample 2 deduct, after that we have to add with this. Okay, what here doing? Actually this is mean, what here standard deviation. Okay, standard deviation this much standard deviation for this much sample size, for this much sample standard deviation for this much sample size, sample 1, sample 2. Okay, then squaring for reduction purpose only, scaling purpose only, then multiply with how much T alpha, then to be actually mean plus standard deviation adding here, that's all. Mean plus standard deviation to be added. T alpha. Okay. This is okay. Then regression. Linear regression. It calculates the equation that will produce the line that is close to as possible to all the data points considered together. Calculate the equation will produce the line to close to the all that is as close as possible to all the data points. All the data points considered together. together. Consider together. Okay. This is described as minimizing the square deviations. This is described minimizing the square deviations, where the square deviations are sum of the square deviations between each data point and the regression line. The difference between each point and the regression line is also called residual because it represents the variability in the actual data. Why it's not accounted for by the equation generating the line. Minimizing the square deviations can be expressed as minimizing errors of prediction or minimizing the residuals. The most important assumptions of the linear regression is the independence and normality of errors in the independent and dependent variables. Other assumptions for simple linear regression are other assumptions for simple linear regressions are data appropriateness, outcome variable, continuous, unbounded, linearity, distribution. The continuous variables are approximately normally distributed and do not have extreme outliers. Homo homoscedasticity, the error prediction are constant over the entire data range. Error prediction constant over the entire data range. Independence. Then the sum of uh, the sum of the square deviation is the sum of squares error or SSE. Sum of squares. The sum of square deviation is the sum of squared deviation. Squared deviation is the sum of squares errors. Sum of square errors equal to summation I equal to 1 to n y I minus y cap square equal summation of I equal to 1 to n yi minus x axi plus b whole square. That is, in this formula, yi is the observed data. yi is the observed data value and y cap is the predicted value. Predicted value according to the regression equation. So here what we are doing, observed data and predicted value. So both are observed data deducted from by predicted value deducted from observed value, then to be square from where I equal to 1 to up to n to be add summation. It is equal to yi predicted. What predicted? Axi plus b whole square. Both whole square. So yi observed data. So predicted value here is different. So axi plus b. This is the predicted here. The variance of S is the variance of S is the variance of S is SXS equal to EX square summation of x square minus summation x whole square divided by n, and the covariance of x and y is